guys, and welcome to your next online math lesson. This is lesson 9.5 in your textbook, page 493. It's called Scientific Notation, and as always, of course, I'm going to suggest you have a calculator, pen and pencil, or paper and pencil handy. Now, here's what gives. Scientific notation. Honestly, not that difficult. However, some kids, I'm afraid, have some bad fundamentals when it comes to working with scientific notation or numbers that are written using scientific notation. So I'm going to try to get you back on track if you've always struggled with scientific notation. I'm going to try to show you how easy this really can be today. Let me apologize in advance if this lesson is a bit longer than normal. I'm hoping it's no longer than 15 minutes. Let's see how fast we can get through this while at the same time I'm hoping that you understand what we're doing at the same time, okay? So first of all, when we write numbers in math class, there are different ways that you can write numbers, and typically we write numbers in a form that's called standard form. And the definition here on the screen shows you that standard form is when numbers are written without using exponents of any kind. So it would be considered like the normal way to write a number. And then I have some examples of some rather long numbers here. What have we got there? 3,500,000,000, right? That's a very long number. It has a lot of digits in it. And actually what it has is a lot of zeros. That I'm going to show you how to make those kind of go away. And then the other number I have written here is 0.00000012. Don't ask me to say that number. I probably couldn't do it if you asked me to. So I'm not even going to try. But obviously it's a very long number. I want to talk about something really quick though. You're going to hear me refer to large numbers and microscopically small numbers. So when I say large number, I mean large in value. Looking at the number here on the left, the 3,500,000,000, this is what I'm going to refer to as a large number. It's large in value, like I wish I had that much money, right? Large, it's a lot. The number on the right, the decimal with 0.00000012, I'm going to refer to that as a microscopically small number. Small in value, meaning if you were going to try to look at something that was this many millimeters thick, let's say like something smaller or thinner than a piece of human hair, right? You would need a microscope to see something this small. It's teeny, 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 tiny in value. So when I say large value, I'm talking about numbers that are very big, like numbers in the millions and billions and trillions. And when I say microscopically small numbers, I mean very, very long decimal type numbers. All right? Because you're going to hear me talk about that throughout the lesson. Okay, so in the real world, in math and in science, when you start experiencing numbers that are really long, like these two numbers are, they have many, 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 many zeros, it does not become effective or efficient to write all those zeros. So they came up with a way to shorten these numbers down, and it's called scientific notation. Scientific notation is when a number is written as the product, whoa, where's it going? Come back. There we go. When a number is written as the product of a number and a power of 10. So believe it or not, I took those two numbers that we were just talking about up above, and I wrote them in their scientific notation form. So 3,500,000,000 in standard form can be shortened to 3.5 times 10 to the 9th power in scientific notation. So this is the scientific notation version of the number that we had written in standard form, 3,500,000,000. And over here on the right, 1.2 times 10 to the negative 7. Looky there, it's a negative exponent on that. That is the scientific notation version of the number that's straight above it, the 0.00000000 whatever 12, right? So these numbers are the same number. They're just written in different formats. So again, I say the reason that we use scientific notation is because it makes the numbers more manageable, more convenient to write, more convenient to work with. And we, like I said, we really only use scientific notation when we're talking about very large numbers, like the distance, how many miles to the moon, how many miles to the sun, or microscopically small numbers with lots and lots of zeros. Okay, so the next thing on the screen in blue says a positive exponent in scientific notation would indicate a very large value number. So if you're looking here at the 3.5 times 10 to the 9th power, that is a positive exponent, and that tells me I'm going to be working with a very large value number, right? And this is that number that was in the billions. And on the other hand, over here on the right-hand side, 1.2 times 10 to the negative 7, I kind of pointed that out earlier. A negative exponent indicates a very small value number. So the fact that that 10 has a negative 7 as the exponent means when I convert this number back to standard form, the decimal's going to be moving in this direction many times so that I have a bunch of zeros here to make this a microscopically small number. All right, so again, positive exponent on the 10 indicates a large value number, whereas a negative exponent on the 10 is going to tell you that this is going to actually be a very small value number, in other words, a decimal. Now, lots of kids come to 8th grade and they, as far as scientific notation goes, they think that the exponent tells you how many zeros to add. And I wish it were that simple, friends. I wish it were that simple. It's not that simple. And sometimes kids are given bad information as they're learning math throughout their elementary and middle school years, and I'm here to set you straight. The exponent does not tell you how many zeros to add. The exponent on the 10 tells you how far to move the decimal. And it also indicates which direction the decimal is going to be moving. So if we're looking at scientific notation numbers, as we are right now on this screen, and I was going to give you the task of turning them back into standard form, right, the quote normal way that we write numbers, the exponent on the 10 tells you how many jumps that decimal is gonna take, and it tells you if it's going to be jumping to the right or if the decimal is going to be jumping to the left. Okay, let's practice what I'm talking about. The directions say express each number in standard form. All right, so obviously we see some things here that are written in scientific notation, and I want it back in standard form, right? The quote normal way we usually write numbers. So let me show you how this works. It's all about moving the decimal and which direction. So this one says 2 times 10 to the 3rd. So the number 2, I don't even see a decimal. Where is it? Where do decimals hide when we can't see them? Right there, to the right of the number. So I look at my times 10 to the 3rd. The exponent is 3. That means this decimal is going to take 3 jumps. Now, is it going to jump to the right or is it going to jump to the left? Well, it's a positive 3, which indicates a large value number, not microscopically small. We're not going to be creating a very small decimal answer here. We're going to be creating an answer in the maybe hundreds or thousands or 10,000s or millions, okay? So this one's going to be jumping to the right. 3 jumps. Ready? Here it goes. 1, 2, 3. Bang. That's where it lands. What do you fill in those gaps? Zeros. I know what you're going to tell me. I know what you're thinking. You're thinking, Ms. Klessner, that's 3 zeros. And the exponent was 3. And you just told me the exponent does not tell you how many zeros to add. And I still maintain that that's true. Occasionally it does work out that way. Occasionally the exponent is equal to the number of zeros that you're going to be adding. But it doesn't work that way all the time. It's not a consistent rule. It doesn't work every time, therefore you cannot use it. So it's not always going to be that way. But yes, for right now, this one did happen to be an exponent of 3, and we did add 3 zeros. So the standard form of that number is 2,000. Okay, look at the next one. 6.8 times 10 to the 5th power. So here's your number, right? 6.8. The exponent's a 5, and it's a positive 5. So we're going to be creating a large value number. That means the decimal's going to jump to the right. 1, 2, 3, 4, 5. Bang. There it is. We better put some zeros in there. How many zeros? 1, 2, 3, 4. 1, 2, 3, 4. 4 zeros. 1, 2, 3, 4. I back it up and put my commas in. 680,000 is the standard form. So look at that. We only added 4 zeros and the exponent was a 5. See, I told you. I told you. Couple more. 3.25 times 10 to the negative 4. Uh-oh. There's the number they give you. Now, 10 to the negative 4, that's going to be a microscopically small number. Decimal's going to move to the left 4 jumps. 1, 2, 3, 4. Bang, it lands there. So it's going to be 0.0000325. As I said, that's a very microscopically small amount. How about this guy? 1.3 times 10 to the negative 3. That's, again, microscopically small. So 3 jumps to the left. 1, 2, 3. That's where it lands. Add 2 zeros, and then the 1, and then the 3. Negative exponent made a microscopically small number, right? A decimal. What's next? Let's go the other way. Let's take some that are written in standard form and squish them down into scientific notation. Okay, we can do that. So for this, it's all about where is the decimal now and where does it need to be in good scientific notation. So if I'm looking at this number, 4 million, where's the decimal now? I don't see one. Well, it's hiding right there, right? It's hiding always to the right of the number. If you don't see the decimal, it's at the far right of the number. Do you know where it needs to be for good scientific notation? It needs to be all the way over between the 4 and the 0. Actually, it needs to be where that comma is. So I'm going to kind of squeeze it in. That's where it needs to be. Good scientific notation places the decimal so that the highest place value being used is the ones place. So, little side note over here on the right. Good scientific notation would be like 4 or 4.5. That would be good. That's good. That's good, right? The highest place value being used is in the ones place. This would be bad scientific notation. That's not good. That's not good. That's bad. Because the decimal really should be one more spot. It really should be there. So if you see something like this, like, well, I'll stick with the 40s. 42.9. That's not scientific notation format because the decimal really should be here. That's where it really should be for good scientific notation format. Nothing higher than the ones place is being occupied by the time you stick that decimal where it needs to be. Okay? So, we got the decimal here on the right, and it needs to bounce its way all the way over to the left. How many jumps is it going to take to get there? Let's count. 1, 2, 3, 4, 5, 6 jumps. Guess what we just figured out? The exponent on the 10. So now my number is 4, or you could say 4.0 times 10 to the 6th power. Why to the 6th power? Because it was 6 jumps to get there. Why? How did I know to make it a positive 6 and not a negative 6? Well, look back at your original number. That was a very large value number. Right, 4 million, that's a large value. And large value numbers have positive exponents on the 6. Okay, let's do the next one. 5,800. Where's the decimal now? I don't see it. It's right there. Where does it need to be? Between the 5 and the 8. Right there. How many jumps? 1, 2, 3 jumps. So, it's 5.8. That's good scientific form. Times 10. And it was 3 jumps. Okay, look at the next one. Well, I see the decimal. Do you know where it needs to be? It needs to go there, between the 7 and the 2. How many jumps? 1, 2 jumps. So what's my new number? 7.2, right? That's good scientific form. times 10. How many jumps was it? It was 2 jumps. But wait a minute. It's a -2. That has a negative exponent because this was a small value number, right? It was a very microscopically small amount, 0.072 or 72 thousandths, right? Very tiny. So that number needed a small exponent on the 10. So does the next one, and so does the one after that. Okay, speaking of the next one, you see the decimal where it is now? Do you know where it should be? I hope you're catching on. It should be there. I'll make it a little bigger. There we go. How many jumps? 1, 2, 3, 4, 5 jumps. So it's going to be 6.4 times 10, -5. And I think this is the last one on this page. Where does it need to be? Bingo, right there. Nothing higher than the ones place. 1, 2, 3, 4 jumps. 9.18. See, nothing higher than the ones place there. Times 10 to the -4th power. All right? Again, this is good form. This makes me like that. This would be bad form. And it would make me like that. Actually, it might even make me angry. Don't make me angry. I think we have a couple more, just one more example, and then we're done. They want you to put these in order from smallest to largest, right? From least to greatest. Oh, well, let's see. I got scientific notation here. I got scientific notation here and here. But this guy is a problem. Bang. We have to convert him. This is like comparing, you know what the phrase is, right? Comparing apples and oranges. You cannot compare numbers if they're not written in the same form or format. So let's take this guy and put him in scientific notation. So 400 in scientific notation. Where's the decimal now? There. Where should it be? There. How many jumps? 2. Positive 2, right? Because it wasn't a microscopically small number. Now that you've got everybody written in scientific form, you can put them in order from smallest to greatest. Immediately, one should jump out to you as the smallest. Hopefully you see it. Do you see the one that has the negative exponent? This guy? Negative exponent, that means microscopically small number. That's really a decimal, right? That's really 0.037 or 0.037. So this is your smallest number because it's got that negative exponent. That's the least. Okay? He goes away. Now they all have 10 to the second power, 10 to the second power, 10 to the second power. So now we just get to look at the numbers. I've got a 3.4, I've got a 3.5, and a 4.0 or a 4. Who would be the smallest? This guy. Next. And then the biggest guy? Uh-oh, I'm almost out of room. This one is the greatest. Okay? So the first way you order them is by looking at the exponents on the 10. And since one of them was negative, it was the least. Then they all had the same exponent. They all had 2's on the 10. So then we just had to look at the decimals. 3.4 is smaller, then 3.5, and then 4 would be the largest. So again, when you're asked to put them in order from least to greatest, you really have to be comparing apples and apples, right? Everybody needs to be written in the same format. Okay? Well, I told you that was a longer lesson. I apologize for that. If you care to look at the assignment ahead of time, this is what we'll be working on together in class. Okay? I'll see you then.